Right, let's go. And feel free to stop and ask me any questions if you're a little bit confused. So today I'm going to be presenting on Markov chain Monte Carlo, which is one of the one of the major workhorses of Bayesian statistics. So I'll be covering the fundamentals. It'll be broken into a multi-part presentation. In this first part, I'll be talking about sampling algorithms and Monte Carlo, so the Monte Carlo aspect of MCMC. And in part 2, I'm aiming to talk about Metropolis-Hastings algorithm, the Gibbs sampler, just Markov chains, and all the other fun stuff. So a little bit about myself. My name is Hong. I'm a SharpestMinds mentee. So my background is actually in business. I did a Bachelor of Commerce at Monash University in Australia, specializing in actuarial science, econometrics, and finance. And I'm also part of the SharpestMinds program. Currently interested in sports analytics, so I'm building a front end for a machine learning application that's predicting tennis matches. And yeah, I dabble in Bayesian statistics occasionally. So the reason why I'm doing this presentation is because I find that the level of discourse that surrounding MCMC is often not so great. If you're not aware, we're going through the Bayesian methods for Hacker's book in the textbook study group. And as the name suggests, it's a book pitched at computer scientists, programmers, and software engineers. So it's great for demonstrating how the PyMC3 package works, probabilistic programming, and introducing you to some cool examples of Bayesian inference. But when it comes to the actual statistical theory, it's a little bit underwhelming. And so I've kind of cherry-picked two quotes from chapter 1, which I thought were kind of questionable, at least since I have a bit more of a formal training in Bayesian statistics. Someone else wants to join. Awesome. Another person. So it's a great book if you want to see PyMC3 in action, but in terms of actual statistical content, it's a little bit, it's a little bit shaky. The reason why such books exist is because the current resources on MCMC are kind of difficult or inaccessible for most, because they're written by mathematicians or statisticians, and some people complain. It's there's a lot of jargon and formalism, kind of wrapping it around, and it is not exactly an easy topic to tackle. So hopefully I can sort of bridge the two worlds, so to speak, and I kind of expressed my feelings about this through this this meme over here. So on one hand, you have the gatekeeping statisticians who just try and make it they don't deliberately try and do this, but they do end up making it a little bit more complicated than it needs to be. And then you have the computer scientists, the hackers, who are blissfully ignorant as to the inner workings of MCMC, but still play around with the stuff anyway. So hopefully my presentation can sort of fill the gap and sort of help the two worlds meet together. So before we get into the meat and potatoes of it, I thought it would be good to do a quick recap of Bayesian inference. So hopefully so this will be good if you're a little bit foggy on the details, or maybe you've never really done Bayesian statistics before. So Bayesian statistics centers around this, the main worldview is that that uncertainty can be expressed through the language of probability, even though there may not necessarily be randomness involved. So it's perfectly valid for you to make a statement that, there's a 70% chance that it rains tomorrow, right? Even though it either rains or it doesn't, and there's no real randomness involved, you can make that statement, at least in a Bayesian sense, because given the current information that you have, your knowledge about the future is limited. So then you express your uncertainty about that using the language of probability. So then you can do this, use these sorts of expressions, and use it to describe hypotheses. And in our interest, in our case as data scientists, we're interested in expressing uncertainty about our model parameters. And so the main workhorse of Bayesian statistics is obviously, Bayes' rule. And in particular, we're using this form. So if I'm moving my mouse around, can everybody see that? Because I don't want to be just waving it around and not getting across. Okay, awesome. So in this case, we're interested in the posterior distribution of our model parameters. And the way we calculate that is using Bayes' rule. So we decompose that into 3 components. The first one being the likelihood of our model. So that is you can think of it as the probability of the the data given our model structure, and then we multiply that by your prior, which is I guess as the name suggests, expresses our prior beliefs about what the model could look like without any data, and then we have the probability of the evidence, P of x, which is the kind of like what the data expresses what the data looks like without any sort of model imposed on it. And so I want to also make you a little bit aware of the fact that the use of PR for probabilities and P for density or probability distributions is sometimes kind of like interwoven in the Bayesian literature. So they're a little bit loose when it comes to this notation. So just be aware of that if you do decide to go and read any further. Sure. Mm-hmm. So that would be like the probability of the model parameters given x. So on the left-hand side, that's the posterior distribution. So you have like some model, you feed it in some data, I guess, and then you output the posterior distribution, and that's calculated using Bayes' rule. Yeah, does that make sense? Okay, all right, no worries. So, and I'll talk about some of the advantages of Bayesian inference. So the first one that I kind of briefly touched on is that probability statements are a bit more intuitive. If you studied statistics in a formal institution, you've probably done like confidence intervals, hypothesis testing, and p-values, and someone else, yeah, and you'll find that frequentist statistics, frequentist results can sometimes be difficult to interpret correctly. So you have to be very precise in the language that you use. So invoking like multiple samples or sort of a convoluted language. So a Bayesian probability statements are a little bit more straightforward in that regard. Advantage number 2 is that you can incorporate information from a sequence of experiments. So using the Bayes rule, so you can, if you have like a sequence of experiments, you can sort of condense all that information into your prior, and then as more data or new, as you conduct a new experiment, as new information comes in, you can update that belief based on the incoming data. Whereas frequentist statistics, you need to be a little bit more careful about how you design your experiments. So all the experiments and all your analysis needs to be laid out sort of from the very beginning. Otherwise, you end up violating statistical assumptions. So, for example, p-hacking is a bit of a problem in the scientific community where you're slicing and dicing your data multiple times until you get a result worth publishing, and then it ends up violating. So you end up compounding the probability of false positives. So Bayesian statistics kind of makes it a little bit easier in that regard. So advantage number 3 is that the results of Bayesian statistics are valid regardless of your sample size. So the frequentist statistics tends to refer to or make reference to limiting results. So for example, the central limit theorem or the law of large numbers. So that is, the results are really only valid when you have like an infinitely large sample, or you make appeals to what they call limiting results. So if you have a really small sample, it's kind of risky to start appealing to those results. So Bayesian statistics is good in a sense that with Bayes' rule, the formula is exact regardless of how large your sample is. And advantage number 4, which is most relevant to us, I guess, is that it lends itself, Bayesian inference lends itself quite well to the paradigm of probabilistic programming. So probabilistic programming maps out the relationships between variables using a computational graph. So whatever it is you're trying to model, all the components are kind of like the nodes of your graph, and the relationships between them are expressed using like vertices. And then so Bayes' rule provides a natural way to perform inference on these models, so you can kind of decompose or deconstruct the relationships using Bayes' rule, and then the resulting posterior distribution allows you to do inference. Okay, any questions about that so far? Hopefully that is at least mostly familiar to you all. Nope. All right. So I'll illustrate this using an example from the chapter 1 of the Bayesian methods for hackers book. So in this example, the author was trying to model the number of text messages that were coming in. So this is like a graph of the actual data over like a 75-day period, and this is the computational graph that you suppose was generating the data. So on the bottom note here, you have the observations being generated by a Poisson random variable with the rate parameter lambda. So if you aren't aware, a Poisson random variable, a Poisson distribution is a discrete random variable, and it is usually used to model count data. And so the rate parameter is the expected number of hits or occurrences within a certain time period. In this case, it would be a day. And the author wanted to incorporate the possibility that there may have been two separate rates, or like a regime shift or a structural break in the rates. So he added another layer of complexity. So you have lambda 1 and lambda 2. So kind of two sub rate parameters. And they had a prior distribution of alpha, which was an exponential distribution. Then tau is the discrete uniform random variable, which is used to model the actual breakpoint. So you can kind of see that here. So the red line is the expected number of text messages received, and so that's kind of the expected value of this lambda here. And then so the tau breakpoint should occur about 2/3 of the way in the data. So that's a quick example of probabilistic programming and Bayesian inference working together. Okay. Does that make sense to everybody? Any questions? Mm-hmm. Yes, and how that generates the data. Yes, you can think of it that way, but then Bayes' rule sort of reverse engineers it, so then you can look at the distribution or express your uncertainty about the parameters given the data. So you're kind of like sort of reversing it in that sense. Okay, so now the question is, where does Monte Carlo, where does MCMC fit into this? So Bayesian inference centers around the posterior distribution for your parameters, right? So let's think about what it might be used for. For example, we might be interested in the expected value of a rate parameter lambda, its variance, or the differences between two parameters, or any sort of high-order function. And so if you remember your statistics, these will require some evaluation of an integral. So we want to calculate the expected value of some function h of our model parameters. In this case, we are treating it as a random variable. So this is therefore an integral of that function of our variables multiplied by the posterior distribution, which we calculate using Bayes' rule. And so then you need to integrate this over the domain of your variables, or in this case, our model parameters. So going back to the text message example, suppose we wanted to find the difference between lambda 1 and lambda 2, or the expected difference between those two given our data. So if you wanted to calculate an exact expression for that, or an analytical solution, you would need to evaluate this integral. So you would take our function, lambda 1 minus lambda 2, so these are our variables of interest. We multiply by the distribution, so this is the posterior distribution for all our model parameters, right, which we calculate using Bayes' rule. And then we integrate that over the domain of all of our variables or model parameters. And so as you can see, this is a really rather ugly expression. So it's a 5-dimensional integral for a potentially very complicated looking function. So trying to calculate this by hand or coming up with some sort of analytical solution is going to be very difficult. And so Monte Carlo allows us to bypass this direct calculation and sort of provide an estimate using simulation. So now I'm going to be talking about Monte Carlo. So I've subtitled this section, very tongue-in-cheek, randomly generating numbers and crossing your fingers. So obviously there is quite a bit more to it than just that. You have to set up your generation process in a particular way. But I've always found it, I guess, almost magical how you can get a very accurate estimate for these really complicated looking integrals by, well, essentially just randomly generating numbers and putting them through some arithmetic. So in this, if we were to apply this to our text message example, so rather than evaluating this integral directly, what we can do is, since we have the posterior, we can sample lambda 1 and lambda 2, and we simulate it as like n observations, or as many as you want. You simply calculate the sample mean, and since we know with the law of large numbers, this sample mean should then converge in probability to the expected difference between lambda 1 and lambda 2. Right, so then, because we are simulating, we can appeal to frequentist methods. Right, so Bayesian and frequentist methods don't necessarily have to come into conflict, as some people tend to describe it as. They can be quite complementary, especially in this regard. And so yeah, that's how Monte Carlo could be used in this example. So in a very general sense, the Monte Carlo is a method for evaluating an unknown quantity for a known system using random inputs. So we set up our system or whatever, we randomly generate our inputs using an appropriate distribution and filter them through our system and look at what comes out from the bottom, so to speak, right? And then you do your analysis on the outputs rather than trying to calculate some sort of analytical expression for whatever you're interested in, because the system itself could be really quite complicated with many dimensions or whatnot. And so this Monte Carlo method works really well regardless of how complicated your chosen function may be, provided you can sample from the posterior. Okay, so that's basically what Monte Carlo is, at least in relation to Bayesian inference. Does that make sense? Okay, do I have any questions about that? Yeah, that's pretty much it. And as you sample, and since it's a simulation, you can sample as an arbitrary amount of points. So then, yeah, as you sample more and more, it actually converges in probability to the thing that you're interested in. Yes, but as you sample more and more, you get arbitrarily close to the absolute truth. All right. So another example you may have seen Monte Carlo used in is the calculation of pi. So this is usually quite a common example used to illustrate Monte Carlo, and I thought it would be worth going through because it's something that you may come across in interviews, but I wouldn't really know. So the idea is that if you would interested in calculating pi, because we don't know what the exact value was, we try and calculate it in relation to things that we do know. So, for example, we know that the area of a circle with a certain radius is pi r squared, and then if we inscribe that circle within like a unit square, so the circle has a radius half, we know the ratio of both the area of both the square and the circle, so the area of the square would be 1, because of the edge length is 1, and then we know that the area of the circle is pi on 4 as well. So then we can approximate the ratio of these areas by randomly generating points within the square, and then looking at how many points fall within the circle, and comparing that to how many points are generated in total. And so that provides us like a proxy or an approximation for the ratio of the two areas, and you can check whether a point falls within a circle or not by just looking at whether it or not it satisfies this inequality. And then so the resulting ratio should be very close to pi on 4. And I think it would be good to illustrate this using an animation. So this one I coded up in Matplotlib. So on the inside you have the blue dots, which are the points that fall inside the circle, and the red dots are the ones that are on the outside. And then so what we're trying to calculate is the ratio of the points inside to the total amount of points. So that gives us pi on 4, or an approximation for pi on 4. Multiply that by 4, and then you get some number which is kind of close to the value of pi, right? So as so I'll run that again. So as the number of samples increases, the the estimate sort of converges to the true value of pi. So unfortunately, it does take actually quite a lot of samples for this to become reasonably accurate. And I think I stopped it at around like 5,000 points because my computer couldn't handle rendering the animation any further. But I think you get the idea. Okay, so that's Monte Carlo, and I've talked about the pi example. Yeah, I can go back to that, sure, yeah. Yeah. Well, I wouldn't really consider this a Bayesian problem exactly. I'm pretty sure you can put a Bayesian framework in that regard, but usually, yeah, I can't really think of how you do that off the top of my head. Yeah. Yeah, so it's an illustration of Monte Carlo as opposed to Bayesian inference, I suppose. Does that make sense? Yeah. Okay. So that's that. So that's Monte Carlo and how given two examples, one like a more general example and one in relation to Bayesian modeling. And so I'm going to be talking about also rejection sampling and importance sampling. But before I do that, I need to talk a bit more about some mathematical statistics. So this is to help you motivate and explain why Monte Carlo in isolation is usually not sufficient, and that's why we have to resort to another sampling algorithm to sort of work together with it. So first thing to talk about is the chain rule of probability. So I'm sure all of you are data scientists, so you're infatuated with the neural networks, and you know very well the chain rule of calculus. So the chain rule of probability is kind of similar. So the chain rule of calculus, we know that the derivative of like dy dx can be decomposed into the product of the intermediate derivatives, right? So you can sort of multiply them or chain them together. So the idea for the chain rule of probability is kind of similar. So we have a joint distribution for the variables of interest, theta1, theta2, and theta3, and then so we can decompose that into a conditional distribution times a marginal, right? So in this case, we are looking at a conditional distribution of theta1 and theta2 given theta3, but we need to multiply by the value of the distribution for theta3 because we don't really know what it is, right? And just as there are many ways to skin a cat, there's many ways to decompose a joint distribution using the chain rule of probability. So you'll see the decomposition being done in many different ways depending on the context or what the author feels is relevant to the current circumstances. So that's the chain rule of probability, and I'll talk briefly about this, the whole joint marginal and conditional distributions, just to hopefully give you a refresher. So a marginal distribution is, in a sense, related to the joint distribution, but we're kind of looking at like a reduced dimensional representation of it in some sense. All right, so we're taking the joint distribution. So the joint distribution tells us how these three variables sort of covary or move together, right? The randomness in a joint sense. But if we want to look at the randomness for theta1 in isolation, so this is our random variable in this context, we need to take the joint distribution and integrate out the other two parameters, or the theta2 and theta3. So in the literature, they'll sometimes refer to it as sort of like integrating out or integrating out the nuisance parameters, right? So then what we're left with is just the marginal distribution of theta1. And then the conditional distribution is very closely related to the idea for conditional probability. So hopefully you all know that. So it's the probability of A given B is equal to the joint distribution of A and B divided by the probability of B. So in this case, for a conditional distribution, we have the conditional distribution is equal to the joint distribution divided by the distribution of the variables that you're conditioning on, right? So in this case, this is a conditional distribution of theta1 given theta2 and theta3. So we take the joint distribution for all three variables and then divide by the marginal distribution for theta2 and theta3. So I think that can be sort of visualized in this graph over here. So on the main or bottom panel, we have a scatter plot sort of representing a bivariate Gaussian. I think it would be nicer if they had like a surface or a mesh to represent the distribution, but I think you sort of get the point. And then so on the left-hand panel, we have the marginal distribution of y. So we integrate it out over all possible values of x, and this is the resulting distribution, right? So represented by histogram and the bell curve. And we also have a similar idea for the distribution for x. We've integrated out over all possible values of y, and then we are left with the marginal distribution for x. Okay, so hopefully that's either a refresher to you or was informative. Do I have any questions about that? Does that make sense to everybody? Okay. So now, one last panel of math before I start explaining why we can't just use Monte Carlo on its own. So, another idea I want to introduce to you is that the concept of a kernel for a density. So we know that for any legitimate probability density function, the density must, the area under the curve should be equal to 1. So if you integrate this, so in this case we're using a normal distribution for θ1, so with mean parameter mu and variance sigma squared. So if you integrate that over the domain of θ1, the resulting output should be equal to, well, 1. So that's by definitional construction. So then we have this idea of a kernel which is proportional to our density. And so in this case, we have absorbed the scaling constant out the front, the 1 over the square root of 2 pi sigma squared, and absorb that into the proportionality sign. So what we're left with is simply the exponent, right? And so this exponent is the core, or as one of my lecturers referred to it, as the sort of guts of the function. So this defines the shape, right? So it controls the displacement, so the mean, and also the general spread of the distribution. So the constant at the front, 1 over square root 2 pi sigma squared, really controls I guess you can think of it, how much it's stretched on the y-axis, right? And so then a very closely related idea is that of the integrating or normalizing constant for your kernel. So as I said before, if you, for any legitimate density, you need the integral for that density with respect to its variable should be equal to 1. So if you take the kernel, then you integrate it with respect to θ1, you're going to get the reciprocal of whatever was absorbed into the proportionality sign, right? So, and you can see that if you take the kernel, you divide by the integrating constant, you're going to get back the original distribution, right? So then if you integrate this kernel divided by the integrating constant, the resulting output should be equal to 1. Right? So then you get back a legitimate density. But most of the time, we don't actually know the full posterior, and what we're working with is usually a kernel. And yeah, make sure you don't confuse this kernel for a density with the kernels used in kernel density estimation. That's quite different. Okay, any questions about that? Nope. Okay, so that's moving on. So now I'll explain why it is that we also need the rejection sampling, importance sampling algorithms, and you can't just use Monte Carlo in isolation. So as I sort of explained before, in most cases the posterior distribution can be quite difficult to find in closed form. So if you take Bayes' rule in the form that we're using it in, so we know that the posterior distribution for our model parameters given the data is equal to the likelihood times prior divided by the probability of the evidence, right? So, and using the chain rule of probability, we know that this likelihood times prior is actually equal to the joint distribution for both the model parameters and also the data. And then so this P of x, the probability of the evidence, is actually equal to the integral of the joint distribution. But in this sense, we are integrating out or marginalizing out the model parameters so that we can get P of x. So this P of x can be thought of as the integrating constant or normalizing constant for our kernel, the likelihood times prior. However, this is, despite how innocuous it looks, it's actually really hard to calculate. So while the joint distribution is really easy in some sense, because you set up your model, so you know what the likelihood times the prior is. But the problem is when you want to calculate the integrating constant, you have to evaluate this integral, right? So you need to integrate out the model parameters from the likelihood times the prior. And so this ends up becoming really problematic, especially if you have a really high number of like model parameters, right? And so this high-dimensional integral is kind of what we've been running away from the very start. So now we kind of run back into the same problem. And so, yeah, so if we don't know the full posterior, we only really know likelihood times prior, which in our case you can think of as our kernel. If we don't know that posterior, we can't sample from it. And if you can't sample from it, you can't perform Monte Carlo, at least directly. And so that's why we have the rejection sampling and also importance sampling algorithms to help us to perform Monte Carlo and calculate those integrals and get those expectations for whatever quantities we're interested in. That way we can perform our inference. Okay, so does that make sense to everybody? Because this is a fairly important slide. Okay, so right, so now I'm going to be talking about rejection sampling. So this is rejection sampling is used when you don't know the full posterior distribution. You only really have the kernel. What you do need instead is a substitute or a candidate which you can directly sample from. And so the idea is kind of similar to your pi calculation example. So you break up the area underneath your candidate distribution into two zones, an acceptance region, which is the subset which falls underneath the kernel, and a rejection region. So then you sample from the candidate and determine whether or not the observation falls within the acceptance region. If it does, you keep it. If it falls underneath the rejection region, you obviously dispose of it. And then so the resulting accepted draws will be legitimate draws from the posterior distribution, even though you don't know it in full form. So I've talked about it in a very broad sense, so I think it would be good if I run through a step-by-step example. So in this case, our kernel, which is the blue curve, is a mixture of two beta distributions. So for a candidate, I've chosen another beta distribution, which is given by the orange line. So the first step is to simulate from this, to generate a draw from this candidate distribution. And then, so in this case, we've got 0.392, right? So this is kind of a single data point histogram representing that. Okay, so we've simulated from our candidate. Now we need to decide whether or not to accept or reject it. So then we draw from another random variable, this time a uniform distribution with the lower bound being 0 and the upper bound being the density of our candidate evaluated at the candidate we've been drawing. So 0.392, right? So this is the upper bound for our uniform distribution. So then we draw a random variable, a realization from this uniform distribution. So in this case, we got 1.384, and so this falls in under our acceptance region, so therefore we decide to keep it. And so this acceptance region, the bottom of that would be 0, and the upper bound for this acceptance region would be the value of the kernel evaluated at the candidate that we had drawn beforehand. And then so the rejection region is the top of that kernel evaluated at our candidate, and the upper bound for that rejection region would be the value of our candidate density at 0.392. So then you repeat this like many times. So this is just for one example. Then you accept and you reject, and you can build these acceptance and rejection regions like this, right? So this is kind of the acceptance and rejection decisions mapped across all possible values over the domain of our candidate and our kernel. So that's how rejection sampling works. Does that make sense to everybody? Any questions about that? Nope. Okay. So that's some of the mathematical details. So I've laid the steps out a little bit more formally, but you can come and look at that in your own time. And so now a few more comments about this. So there's one thing I actually left out when choosing a candidate. So you need to make sure that you, when you're building those acceptance and rejection regions, you need to make sure that you scale it by a factor m, right? So in reality, this kernel isn't scaled correctly because we're missing the integrating constant, right? So the scale could either be too large or too small for a legitimate density. So then I've sort of sketched this out against the actual density for my candidate, right? So then what I've done is I will still be sampling from this density, but when I'm making a decision to accept or reject, I'm basing it on a rescaled version of that density. So I multiplied it by, I think the constant here was 3.5. So that's m in this particular case. And so ideally, m should be chosen to be as small as possible, so we're maximizing our sampling efficiency, right? So you don't want to maximize the probability of acceptance and minimize the probability of rejection. And it's very important that you actually do cover the you scale the candidate so that it does cover the kernel, so that you have enough area to work with. So you can think of it as like when you're baking something, right? So you need to have enough dough to cover the cookie cutter or the mold that you're using, right? It doesn't matter what sort of shape the cutter may be, as long as there's enough dough to completely cover it, you can get the cutouts of the right shape. So this particular example, our kernel is our cutout, and the area underneath the rescaled density is really sort of like our dough, right? And some more comments. So the domain for the candidate and also the kernel should be the same. So meaning that, so you don't want the candidate's domain to be too large. The reason for that is because, well, then you'd be sampling from the parts of the candidate which don't really bear any relevance to your kernel, so you'd be generating samples and then throwing them away immediately. And kind of the same idea for if you don't want the domain for the candidate to be too small either, because then you would be there would be areas from which the kernel that you can't really sample or access. And the shape for the two kernels should the kernel and the candidate should be kind of similar as well. So in this case, we have a relatively flat kernel, so I've chosen a relatively flat candidate density, right? So we don't want, so I wouldn't be choosing something particularly peaked with like a very sharp spike, because then I'd have to rescale it by a large amount, and then there would be a lot of area underneath the curve, which would lead to rejection. So we want to make sure the shapes sort of roughly match each other. Yeah. Okay, so that's that. Do I have any questions about that so far? All right, so now I'm going to be talking about importance sampling. So then importance sampling is kind of like rejection sampling. So with rejection sampling, you generate samples and then sort of put them into your Monte Carlo estimator. So importance sampling sort of combines those two steps together. So it works under sort of the same conditions. So you have a kernel, and then you have a candidate density, which you can sample from directly. And so the way you approximate the expectation, which you're interested in, is using this rather nasty looking formula here. And so while it can look, I think, really quite intimidating, there's a lot of meaning behind each of the components. So here you can think of it as we're approximating this expectation using a sample mean. So that's like, I suppose, normal Monte Carlo. But remember, since we're drawing these from a candidate density rather than the full posterior, so we're drawing these from G rather than P or Q. So the weights, so the distribution for these states is going to be sort of wrong. And then so this weighting function, so this Q over G sort of either sort of corrects for these imbalances. You can think of it that way. So for example, if you had a value for theta, a sampled value for theta, which was very likely to be sampled from G, so then the associated likelihood evaluated at that G would be quite high. So then this denominator value in the bottom would be quite high. However, if that value were unlikely to be sampled from the true posterior or the kernel, then the pseudo likelihood associated with that kernel evaluated that particular value of theta would be low. So you have a small number being divided by a relatively large number. So the associated weight for that theta, and then hence that evaluation of h would be small. So we're kind of doing a weighted sum for our h's, or a weighted mean rather. And then so you can think of it in the reverse case, if we had a value for theta which was unlikely to be sampled from G, but very likely to be sampled from Q. So then the likelihood for G would be relatively low, and the likelihood for the pseudo likelihood for Q would be relatively high. So then you have something small being divided, something large being divided by something relatively small. So the overall weight would be actually quite large attached to that H. So then that's how you sort of correct for the imbalances between G and Q. And so this Q divided by G is what they refer to as the importance weights. So these are the importance weights which you evaluate at the sampled thetas, which you sample from this G as opposed to the posterior distribution. And then so on the denominator, we simply have the mean of these importance weights. So the reason why we do this is because, remember, this Q, this integral, the integral of Q doesn't equal 1, so it's an illegitimate density. So we're kind of correcting for that by dividing by the mean of the weights here. So that's how you can sort of interpret this denominator. So that allows us to build an estimator for this expectation, which is ultimately what we're interested in finding, right? And so that's importance sampling in a nutshell. And I've given a slide here. It kind of goes through the mathematics of it. And gives you a bit more of a formal derivation to the formula, but that's something you can, perhaps we can come to that if there's any questions, but I think you should go and revisit that in your own time. Okay, so that's importance sampling. Are there any questions about that? No? Okay. So that's so now we've covered Monte Carlo, we've covered rejection sampling, and also importance sampling. So now the question is, where do the Markov chains kind of fall into this? So the problem with, let's just say, with rejection sampling is that it can actually be quite difficult to find a good substitute distribution to sample from. And this problem sort of compounds as the number of dimensions increases. So so the sampling inefficiencies will compound with the number of dimensions. So you can think of it this way. So if your probability of acceptance in any dimension is like 95%, this will decay exponentially as you multiply it together as the number of dimensions increases. So that's what they call the curse of dimensionality, which I'm sure many of you will be quite aware of. And then so Markov chains combined with Monte Carlo allow us to deal with this problem. So that's what I'll be addressing in part 2. So that's where the MCMC kind of finally comes into play. So two main algorithms for MCMC. So they are the Gibbs sampler and also the Metropolis-Hastings algorithm. So the Gibbs sampler works by breaking down the distribution you're interested in sampling from, and breaks it down into like conditionals, right? So rather than sampling from the joint distribution in one go, you sample from each of the conditionals and sort of iteratively sample and cycle through each of the conditionals. Then that produces a legitimate draw from the joint posterior. Metropolis-Hastings algorithm is, I guess you can kind of think of it as like somewhat similar to the rejection sampling, in that you have like a candidate density which you sample from, but you set up your sampling algorithm in such a way that as you continue to draw more and more samples, this candidate density will then converge in probability to the actual posterior. Right? So that's where the Markov chains and the Markov properties really comes into play. So I'm just giving you a brief explanation of them, but I'll cover them in more depth in the second part. The problem, I guess, or the disadvantage of these MCMC techniques is that they tend to produce dependent samples, whereas like things like rejection sampling, they produce independent samples. MCMC algorithms are dependent due to the Markov properties. So the total information contained in them is actually a bit possibly quite a bit lower than you might expect. However, given the how problematic the curse of dimensionality is, this is usually considered a good trade-off. Okay, so that's the end of my presentation. So I've given you, so here are some additional links that you can kind of look at. So I've got my GitHub for this presentation and 2 books which I think are good. So I kind of poked fun at Bayesian methods for hackers at the very start. But I think it's a good book if you want to get started and see how PyMC3 works in practice and see some interesting examples. But if you want a bit more a rigorous approach to the theory, you can look at Bayesian data analysis, which is by Andrew Gelman. And so that, I think, is a completely open source textbook now. So I think it's a great reference. Okay, any questions? All right, I'm going to stop recording now.